Everybody, we're back for the second half of related rates, the cone. We're on the back side of our note sheet now with a new problem, and this problem has two parts, A and B. So let's just start in by reading the problem. Sand falls from a conveyor belt at the rate of 10 cubic meters per minute onto a conical pile. The height of the pile is always 3/8 of the base diameter. How fast is the height of the pile changing when the pile is 4 meters high? Okay, so you know I always start with my diagram. This time, my diagram will be a cone because it is falling onto a pile that's cone-shaped, conical pile. But I'm going to do point up because if we think about sand falling onto a pile and it's cone-shaped, then it's going to have to look something like this. Okay, all right, and we know that the sand is falling on here to the pile, and the height will be growing, the radius will be growing. Okay, so what are our givens? Well, the first number I stumble across when I read is this 10 cubic meters per minute. So what is that? Well, just like the problem we did before, I look at the units. Cubic meters measures volume. Minutes measures time. So I'm going to say that they gave me 10 cubic meters per minute because they wanted to give me how quickly the volume of this was changing with respect to time. So we are growing this sand pile 10 cubic meters every minute. That's a change in volume. Okay? The next number I stumble across is this 3/8. So let's take a look at that. It says the height of the pile, so H, the height of the pile is equals 3/8 of means multiply the base's diameter, this guy right here. So the height of this pile, this height, is always equal to 3/8 of its diameter. So it's a fraction of its diameter. Okay, so it's unlike, as I process this problem, this is not like the tank we had earlier with the water inside of it. It's not like we had a cone here growing within a cone. This sand pile is growing on top of itself. So I'm not going to draw some other cone inside here. This just is what it is. But hopefully this little snippet right here is going to help us get through the problem. Okay, so what do I need? Where's the need? Where's the question mark? All right, it's right there. So how fast is the height of the pile changing? All right, so how fast is the height changing? The change in height. How fast is the height changing with respect to time? I can't talk right now. I'm making a video. Okay. So how quickly is the height changing with respect to time? Sorry, I just got interrupted. How quickly is the height changing with respect to time? And that will be measured in meters. Height is measured in meters, time in minutes. And how fast is that changing when the pile is 4 meters high? So when the height is 4 meters. Okay? How fast is the height of the pile changing when the height is 4 meters? So we need an equation. Actually, you know what? I should have put this. Should have really put that over here. That's more of a given. At the moment the height is 4 meters, how quickly is this changing? Okay, so the equation. I'm going to steal the equation from the front side of this worksheet because it's volume of a cone again. Because I need an equation that's going to relate volume, height, and that's it. Volume and height. So volume of a cone is 1/3 pi r squared h. Okay, so volume is 1/3 pi r squared h. Now I'm going to need to do some side work because, like the last cone, I don't have any information here about r or dr dt. So I'm going to need to get rid of this r so that my equation is in terms of h only. So my side work, well, let me look at this equation right here. I'm going to use this equation they gave me to help get r in terms of h. So I'm going to bring that down here. So h equals 3/8 d. Now I want to try to bring r into this, so I'm going to write it as h equals 3/8 times diameter is 2 radii. So I'm going to replace diameter with 2r. If I multiply 3/8 times 2, 3/8 times 2 is 6/8, or if I reduce that, that's going to be 3/4 r. And now, last step, I need to solve for r in terms of h, so I'm going to divide both sides by 3/4 or multiply both sides by 4/3. That would be another option. So r is equal to 4/3 h. Now, I take that r in terms of h and I bring it back up to my equation. So volume equals 1/3 pi, here's my r, 4/3 h squared times h. And if I do a little exponent work here, volume is going to be 1/3 pi times 4/3 squared is 16/9, and h squared is h squared, plus I have that extra h on the back. And now just cleaning it up one last time, 1/3 times 16/9 is 16/27 pi h cubed, because h squared times h is h cubed. Okay. I'm going to click and drag that formula down to differentiation. V equals 16/27 pi h cubed. And now I'm going to implicitly differentiate with respect to time. So the derivative of v is 1 dv dt. Don't forget that on the back. And now here we are again. This is another power rule. I need you to think of 16/27 pi as just a constant in front of your h to the third. So using power rule, we'll bring the 3 to the front. 3 times 16/27 pi, and then reduce the exponent by 1, and tack on the dh dt to the back. So cleaning this up, let's see, 1 times dv dt is just 1 times dv dt is just dv dt. And 3 times 16/27, well, 3 goes into 27 9 times, so I'm going to call that 16/9 pi h squared dh dt. And if you remember up top, I was looking for dh dt. That's what I needed. So I'll solve for dh dt by dividing both sides by 16/9 pi h squared. So dh dt equals dv dt all over, kind of running out of room here, all over 16/9 pi h squared. Okay, now I'm ready to plug in and solve. So I wanted the change in the height of this pile with respect to time when the height was exactly 4 meters tall. So I'm going to plug in. I'm going to just go over on this side here of my dh dt. My dv dt is 10 over 16/9 pi times 4 squared. And into the calculator, I'm going to put that. So I've got alpha y equals, you see that there, 10 on the top, alpha y equals 16/9 pi, parentheses, 4 squared. So it looks like 0.112. So I'm going to just put this here, 0.112 meters per minute. 0.112 meters per minute. Now, my sentence to kind of conclude, what I'll do is I'm out of room here. I wrote too big, so I'm going to write it up here if that's okay. So I'm going to say, at the moment, the height of the sand pile is 4 meters. So at that exact moment, because we know the moment matters, when it gets toward the top, it won't be growing as quickly because we're coming to that point. When you're low in height, it's going to take a little bit longer because look at the spread here. So the moment matters. So at the moment, the height of the sand pile is 4 meters. The pile's height is increasing at the rate of, sorry for my handwriting, at the rate of 0.112 meters each minute. That will change as the height changes. When the moment in time changes, so will the dH dt. Okay, and the last part of this video here, part B, how fast is the radius of the pile changing when the pile is 4 meters high? So now they did bring in radius. This is the first one that brought in the radius. So what I need, now notice, I'm not going to redraw the diagram in the givens because this is the same problem, but I need something new. I need how fast the radius is changing. I need the change in radius with respect to time. That's what I'm looking for in meters per minute. Okay, so what's my equation? Well, I feel like my equation, well, it's the same diagram, so shouldn't my equation be the same as up here? And remember my final equation, V equals 16/27 pi h cubed. There's my equation. Here's the problem. It doesn't have an r in it. It's got an h in it. But that's okay. I can just tweak my side work. See, my side work said that r, and again, I'm taking the last step of all this, r was equal to 4/3 h. Remember that from up here? Well, if r is equal to 4/3 h, then h is equal to 3/4 r. And just like that, I can turn my equation into volume in terms of r. So it'll look like this. V equals 16/27 pi, let's replace h with 3/4 r, and then cube it. We got to tweak that, clean it up. 16/27 pi times. Okay, 3 to the third power is 27. 4 to the third power is 64. And r to the third power is r to the third power. And if I do one more step, see what'll happen is these 27s will drop. That's kind of nice. And 16 goes into 64 4 times. So I can write this as 1/4 pi r cubed. Very nice. See, now I have v in terms of r. So now I can work with dv dt and dr dt. So let's go to differentiation. Well, the derivative of v is 1 dv dt. And now using my power rule, I'm going to take 3 times the 1/4 pi. I'm going to reduce my exponent by 1 and make it r squared and tack on dr dt. Okay, so cleaning this up, I've got dv dt equals 3/4 pi r squared dr dt. And I want to solve for dr dt. So I'm going to divide both sides by 3/4 pi r squared to cancel that out. And I'm going to divide this side by 3/4 pi r squared. So my final equation is dr dt equals dd dt all over 3/4 pi r squared. Okay, so plugging in, dv dt from up above is still 10. That didn't change. 3/4 pi, and now I need my radius squared. Now, here's the last little glitch in this problem. They didn't tell me the moment in terms of radius. They told me the moment in terms of height. Look at this question. How fast is the radius changing when the pile is 4 meters high? So they're still giving me the moment when h is 4. Well, I don't have an h here. So I have to find the radius of this pile at that moment. So I have to create my own radius. Well, it's not too hard to do because if we go back here to some of the side work, you see that the radius, when h right here, the radius when h is 4, if I just plug a 4 in there, is going to be 4/3 times 4, which is 16/3. So that's what I'm going to put for my radius, 16/3. So I'm going to put this into the calculator and I will be done. So I've got alpha y equals 10 on top over alpha y equals 3/4 pi, and then I got to put 16/3 squared. And I am getting dr dt equals 0.149 meters per minute. Final answer. Okay, so my sentence, and I truly am out of room. Where am I going to put this sentence? I'm going to squeeze it down here. Okay, so I'm going to say, at the moment, the height of the sand pile is 4 meters, because that's the way they gave it in my wording here, so I'll keep it the same. So at the moment, the height of the pile, the height of the sand pile is 4 meters. The radius of the pile is increasing at the rate of 0.149 meters per minute. Sorry for the small handwriting, but I evidently wrote too much. All right, so hopefully that makes sense and you're all caught up from being absent or missing class, and we'll see you for the next video.